Good afternoon, class. In today's video, what I wanted to do was to go into a little bit more detail on nuclear fusion. And I know I have a lot of details that are in the packet that I provided for you on nuclear fusion, but I thought I'd do a little bit more math in this one just to show you how we get nuclear fusion and what kind of energy we could get from nuclear fusion. So we start off with the equation. You have deuterium plus deuterium will give you helium plus some energy. And that's a nice, simple equation, of course. But of course, we want to know, how do we even, first off on the conceptual side, how do we even get these deuteriums to collapse into helium? You know, how do we even get this fusion to occur? So that's one side. On the other side is a little bit of math on how much energy do we even get out of this? Is it even worth doing this thing called nuclear fusion in the first place? So here we go. Here's where we get started on this. So when the nuclear fusion will always occur when the electromagnetic force is overcome. There are many ways to do this, actually. The most natural way of doing that is through gravity. All you have to do is get a bunch of dust and have it gravitationally collapse on itself, and what you'll get is a star. A star is a big burning nuclear furnace where there's nuclear fusion going on all the time. In fact, the best example of it is right up in the sky. It's our sun. That's the most shining example that we have of nuclear fusion going on right now. Of course, if you don't have a star that you can just do nuclear fusion with, then you need to have some other ways to make nuclear fusion on a much smaller scale. Some people would call this microfusion, where you could like have a fusion reactor, say, in your watch or something. But that's not going to be as practical first, because first what we have to do is we need to take the sun, a process that goes on in the sun, and bring it down to something that we can do on Earth, because, for example, our sun is about 1,000,000 times more massive than the Earth, so there's no way that we could use gravity alone to get us nuclear fusion. But there is another way, and we can use heat. So what we do is we take this thing called a tokamak reactor, which is basically a whole bunch of magnets and a whole bunch of what we call a magnetic bottle, where you have a magnetic field that confines all of your hydrogen in there into this one area, and you spin it around the tokamak area, and it gets hotter and hotter. Eventually, what happens is the hydrogen atoms or the deuterium atoms will keep getting closer, and they'll get pushed apart by the electromagnetic force. They'll get closer and then pushed apart. As they get hotter, that eventually they will they'll get close and push apart, close and push apart. More energy is pumped in, they'll get closer before they get pushed apart. Eventually, they'll be coming together so fast that they will fuse together. They'll get so close that the nuclear force will take over, and they will fuse together. So that's one way of doing it. That's I guess the easier way of doing it, because we've been doing this method for several decades now. The other one that was a little bit later on in development was this laser method, which, you know, is always fun. So and the reason we can do that is because we take a bunch of lasers and pump energy into the deuterium atoms really quickly, so that they have all this energy that forces them together. Again, we're just forcing them together. So if you can crush them together using gravity, you can force them together, have them smash into each other, and that overcomes the electromagnetic force through heat. Or you can just put all that energy in directly using a laser. And that's what we get with what we call an inertial confinement reactor, where we take lasers. This is a very simplified version, but you have like a little sample in here of deuterium atoms, and you fire lasers into the inertial confinement target, and those lasers will force all of the atoms in there to fuse together, because they'll get so close that they will fuse together. So those are the ways that you can get nuclear fusion. Now, why would we even do this? Isn't there plenty of energy available to us? And the answer is yes, there is, but nuclear fusion does have some advantages, because the amount of energy is quite large. So let's go over that, because that's where this one comes in, because this is a nice general idea. Oh, we have some energy, great. But do we know how much energy is released? And that's what we're going with. To make things a little bit easier, I didn't want to keep writing the mass of hydrogen is something and put it in kilograms, because I'd be using a lot of scientific notation, and my all of the answers would get stretched out way over here. So what I did was I said atomic mass units are AMUs. So the mass of hydrogen would be 1.00797 AMU. Then of course the mass of deuterium, which is what this is, because hydrogen would be 1,1. Deuterium is 2,1. So deuterium would be 2.014 AMU, and the mass of helium is 4.00260 AMU. Now, of course, you might think, oh, well, that's not that much of a difference, but it is. And because of that difference, we can use E equals mc squared to actually figure out how much energy is going to be released. So I went through a few mass equivalencies here. So 2 deuterium atoms combined into a helium atom gives you 4.0026 AMU plus 0.0254 AMUs. And of course, that doesn't seem like a lot. It's not even an atomic mass unit. And of course, it's not a lot because it's 4.21217.8 approximately times 10 to the negative 29th kilograms. So again, very light. However, this is important because this is only when 2 deuterium atoms combine. And of course, we can now figure out what the energy released in that is. We're using E equals mc squared. We would say, okay, multiply all of this out and you get about 1.35 or 1.36 times 10 to the negative 12 joules per reaction. So every time 2 deuterium atoms come together, they release about 1.36 times 10 to the negative 12 joules. Now that doesn't seem like a lot. That seems like quite a small amount of energy, right? However, deuterium is very, very light. So that means if you took just a kilogram of this stuff, you might be able to say, okay, well, how many, because now you can ask, okay, well, that's only with two deuterium atoms. What if I had more than 2 deuterium atoms? What if I had just 1 kilogram of deuterium atoms? How much energy could I get out of that? And the answer is quite simple, because we would just have to know, in 1 kilogram of deuterium, you can have 1.5 times 10 to the 26 reactions, because there are 3 times 10 to the 26 atoms in 1 kilogram of deuterium. So then you would say, okay, well, let's run the equation again. E equals the number of reactions that can take place times the energy per reaction, and using our factor label method that we were so fond of, what we get is about 2.18 times 10 to the 14th joules. Now that is actually a significant amount of energy, and that's only from 1 kilogram of deuterium. Can you imagine if you had a tokamak right here? This has way more than a kilogram of deuterium inside of it. So this thing could produce huge amounts of energy. And of course, if this produced it every, let's say you burn through a kilogram of deuterium every, like, say, minute, right? You divide this by 60 to figure out how many watts this could put out, and the answer is it's in the gigawatts. Actually, no, it's not gigawatts. It'd be terawatts. So basically, it would produce more power than any reactor that we have currently. Any coal reactor, basically any nuclear fusion, even a nuclear fission power plant, couldn't produce this much energy. This is it's about 5 times as much as a nuclear fission reactor. So, I mean, if you're looking for energy efficiency, this is the way to go. Also, one thing to keep in mind, when you've got this energy thing, when you got this equation, you've got hydrogen. None of that's radioactive. At the end, you've got helium, which is also not radioactive. You've got energy. This is in the form of heat. So, well, that heat's not radioactive. So notice in this equation here, there is no nuclear waste. There's nothing that's going to be polluting and radiating everything, for the rest of our lives or anything like that. None of that's going to occur. All you'll have is just a bunch of helium at the end, which potentially you could sell to the helium balloon industry to help them out, because it's not like we have a whole lot of helium left on Earth anyway. So that's something to think about. This is where what you can get from nuclear fusion. Now, to be fair, it is hard to build a nuclear fusion reactor just on its own, because to build it, we actually need to be able to produce this kind of technology with like a tokamak or an inertial confinement reactor. These are not easy to build. So on the front end, it's very, very expensive to get this kind of energy out. But it's very easy to clean up. there is no cleanup. You just take a bunch of all of this helium, use it, in helium balloons or something like that. None of it's radioactive, and that's it. Then you're done. That's the complete use of a helium power, of a nuclear fusion power plant. And of course, you might also wonder, where do we get deuterium? Is it found naturally somewhere? And the answer is yes, it's in seawater. So, especially for those, if you're watching this and you know that where I'm filming this right now in Hawaii, which is surrounded by the Pacific Ocean. So, think about that as in terms of where could we build nuclear fusion reactors, where as long as we have the technology to build it, all we need is seawater, and we can get almost all the deuterium we're going to need for possibly millions of years. So I wanted that to come into your heads. Think about that as we consider what's going on with nuclear fusion. So good luck in your studies. May the force be with you.